Welcome back, everybody. So it is now lecture 9, even though we haven't gone anywhere, and it's the same day as lecture 8. And we're going to be covering a different topic, which is going to be very important moving forward. Let me go ahead and share. This is going to sound really fancy, so you can brag to your friends and family that today you learned matrix vector calculus. All right, that's what we're going to be discussing today, matrix vector calculus. So let's start by motivating why we're going to need this, right? So I'll point out two fun kind of points. One of these is in this class, we are absolutely going to need to know how to take an equation, which is a vector or a matrix equation, and take the partial differential equation, or the partial derivative of that equation. So let's say hypothetically, and I'm going to erase this, but let's say that we said well, here's a great example, actually. The two-body problem, two-body equations of motion. R double dot is equal to negative mu over R cubed R. I don't know why that took me a second to write. This is a vector differential equation, right? We have a vector, second derivative is some function of a vector and some other things that are happening to a vector. Now, suppose I said find the derivative, the partial derivative of R double dot with respect to R. What would that look like? And by the end of today's lecture, we will be able to answer questions like that. So we need to be able to say, if we have some gnarly equation with a bunch of matrices and vectors in it, and we now need to start taking derivatives, do we have the skills and tools necessary to accomplish that? So that's what we're going to be discussing with matrix vector calculus. So here we go. There we go. So we're going to start. We will define, and this might seem kind of obvious, but we're just going to get it on paper, right? Define a matrix A as having elements A, I, J, where the I is the row and the J is the column. So A is A11, A12, A21, A22 in the case that it's a 2 by 2. Okay. The differential of a matrix is defined as the matrix of differentials of its elements. So what do I mean by that? dA is just dA11, dA12, dA21, dA22. All right, so far so good. This should pass a sanity check so far. From this, it's obvious, hopefully obvious, that the differential of A plus B is just the differential of A plus the differential of B. And the differential of A times B is the differential of A times B plus A times the differential of B. Right? And so we remember this should look very familiar from our derivative rules in calculus, either in high school or early in undergrad, right? So the derivative of two things being added, derivative is a linear function. And then if two things are being multiplied, it's the derivative of the first times the second plus the second times the derivative of the first, right? So now consider the scalar function f of the scalar variable x. So the way we would write that is f of x maps from R, the real numbers, onto the real numbers. So f of x is some function that takes a real number in and gives you a real number out. That's kind of the fancy way of saying that, right? Then the derivative of f with respect to x, we're going to write that as f sub x. Or if we rewrite this thing a little bit, we would say the differential of f is f of x times the differential of x. Same equation, just written out this way. All right. Still with me? Good so far. Next, consider a scalar function g of the vector, not just any vector, but it's specifically, let me erase this, the n by 1 column vector x, which is x1 to xn transpose, right? Because it's a column vector. So we would say that g of x maps from n-dimensional space onto one-dimensional space, because you're taking n inputs and you only get one single output, right? So g of x with a little vector over it, there you go, is some function which maps from n-dimensional space onto one-dimensional space. Okay, so we could say that the output g is g of x1 and all the other terms up to xn. Okay. From the chain rule, remember the chain rule? From the chain rule, the differential of g is g sub x1 dx1 plus g sub x2 dx2 plus all the way out to g sub xn dxn. It's the same exact equation that we had before with f, right? So we're saying the differential in the output g is the partial derivative of g with respect to the first input times the differential of the first input plus dot 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 plus the partial derivative of g with respect to the nth input times the differential of the nth input. Right? So the same exact thing we had before. It's just in a higher dimensionality in this case. So let us define some vectors. Let us define gx with an overbar is gx1, gx2, dot, 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 gxn, and it's going to be a column vector. I'm sorry, take it back, not a column vector. This is a row vector. Right? And then we'll also say the differential of x is all of those differentials added up. So that's dx1, dx2, all the way to dxn. And this is transpose. So this is going to be a column. Wow, can't write that. This is a column vector. There we go. So therefore, we can say that g, the differential of g, which is a scalar, right? Because g is a scalar. The differential of g is gx dx, right? It is a row vector times a column vector. It is essentially the dot product of those two gives you your differential g. Or in plain English, and this is the punchline, the derivative of a scalar with respect to a column vector is a row vector. That's the big thing to take away from this section, right? The derivative of a scalar with respect to a column vector is a row vector. All right. So far, so good. Moving on. This is going to seem a little bit disjointed, like we're going in a bunch of different directions, but it's all going to come together by the end of lecture here, so bear with me. Now, suppose that H is a m by 1 column vector whose elements are functions of the n by 1 column vector x. Okay, so what does that mean? H, which is a vector, is h1 of x all the way to hm of x, where x itself has n elements. So each term in H is some different function of all of the elements or some combination of the elements in X, right? So in that case, the differential of H is, which is just dH1 all the way to dHm, is h1 sub x1 dx1 all the way to h1 sub xn dxn. And this is hm sub x1 dx1 hm sub xn dxn. So you have to essentially, to properly take the derivative of h, you were looking at a matrix where you have to consider the partial derivative of all of the terms in H with respect to all of the terms in X. So the first element of H with respect to the first element of X, all the way to the first element in H with respect to the nth element in X, down to the mth, as in Mike element in H, with respect to the first element in X, and then the Mike with respect to Novemberth element. So putting this in a matrix, we would get this. DH is equal to, I'm going to write this as H1 sub X1, H1 sub Xn, HM sub X1, HM sub Xn. And there's our matrix. And this is going to be dx1 all the way down to dxn. So this is a m by n matrix, and this is an n by 1 matrix, and it should be clear that dh is an m by 1 vector. And so if we wanted to, we can write this as dh is equal to, and I'm going to write this as h sub x with 2 overbars to be very clear that we are in matrix land. And then I'm going to write this as dx. Or the punchline, which is going to be very important for us moving forward, the derivative of a m by 1 column vector with respect to an n by 1 column vector. So the derivative of a vector with respect to a vector is a m by n matrix. And we will absolutely need this when we are getting to, oh gosh, I'm trying to think, what homework? Definitely homework 5 is going to rely on this pretty heavily, but we need to kind of lay the foundation now. As a matter of fact, I think we're going to be taking some partials even in homework 2, so this is going to be useful. All right, now what about a row vector, right? Let's move on to the next idea. We're going to use the letter P, which is some P1, P2, all the way to Pm as in Mike. Let P be a row vector which is made of functions. So each P is a function of the n by 1 vector x, right? So x is back, right? So I'm going to kind of skip going through and showing you all the steps. We're getting better and better at this, right? We're going to say that D, you could essentially treat P, if P is a row vector, then P transpose is a column vector, right? And so this would look like this. P with respect to X transpose dx, where this is an m by 1, this is an m by n, and this is an n by 1, right? So we're just piggybacking off the work we already did. We're just saying, look, if it's a row vector, we're just going to transpose the thing. So dp not transposed is, if we're going to rework the right-hand side of this equation, you can apply the transpose to both elements of the right-hand side, but we have to change the order. So this would give us dx transpose and then p sub x double arrow, where this is now a 1 by n and this is an n by m, and that would make this a 1 by m. So it's always good to check your dimensions of your matrices. So the punchline here is the derivative of a 1 by m row vector with respect to an n by 1 column vector, let's say vector, it's clear from the dimensions, is a n by m matrix. All right. So far, so good. So far, it's been just, yep, this is how this works. This is how this works. This is how this works. Thanks for bearing with me. Next, we're going to start using this to actually solve some problems. So let's take the differential of the inner product. The differential of the inner product. Okay. So the inner product being the vector dot product, right? Now we can evaluate the differential of the inner product. So suppose that some vector A, which is a row vector, times some vector B, which is a column vector, is some scalar C. Because when we have a row vector times a column vector, that gives us a scalar, right? So what this means is, okay, if we were to take the differential, the left-hand side would look like this. dA, still a row vector, times B, plus A dB is equal to dC. Okay. But now remember what we've already discussed. If you have a scalar, right, the differential of a scalar is C with respect to x dx, right? The differential of a scalar is a vector. Similarly, the differential of the vector A, which is a row vector, is going to look like dx transpose times A sub x double over bar. That's going to give us a matrix. And similarly, dB is going to look like B sub x double over bar dx, also with the vector. So this is just piggybacking off of the last couple of things that we've discussed. All these are going to come together now. So let's take this equation and rewrite it a little bit. I'm going to say that dC, which is a scalar, is dx transpose ax double over bar b. So all we're doing is making a substitution, plus a bx double over bar dx. And it must be the case that if the left-hand side is a scalar and the right-hand side is two things added together, that each of these terms must be a scalar. All right. So far, so good. And we also know, here's a little fun, cheaty trick, right? We also know, remember, that a scalar transposed is unchanged, right? The whole idea of a transpose is changing a row vector into a column vector into a row vector, a m by n matrix into an n by m matrix. But if you just take a scalar, like the number 4 transpose is still the number 4, right? So I'm going to say this, dc transpose, which is just dc, is equal to what? Well, if we transpose each of these terms, remember that that flips the order. So the first term becomes B transpose A sub x transpose dx plus the second term. If it's a scalar, we don't have to take the transpose of this term. We can leave this as A bx dx. That's perfectly allowed, right? So what we can then say is this, dc, we'll think of it this way, c with respect to x, which is a vector, is b transpose a sub x transpose plus a b sub x. Right? So this is a row vector. This is a matrix. This is another row vector, and this is a matrix. Well, that's going to land us as a row vector. Okay. So what that means is C, which this should make some sense, right? C is a scalar, and if we're taking the differential, that's going to get us a row vector. So this is not a new idea, right? So we can take the same idea. We've now taken the dot product and explored the differential of the dot product. We can now apply this to other common vector operations. So we'll do another example here, right? We will now, I think if you're like me, the abstract side of things gets a little bit weird after a little while, and the more examples, the better. So here comes some examples. So now apply these ideas to common vector operations. So let the vector A be a column vector, A1, A2 to AN transpose, and we'll let the matrix A be A11 to A1N to AM1 to AMN. And this is just any vector A and any matrix big A, right? So here's an example. Find dy dx for the case that y is equal to some vector A transpose x. So this is really dy dx with a little hat on it. So we know now that we have a vector equation, and it's time to start taking some derivatives. Okay, so we can think of it this way. Y, which is a scalar, plus some differential element in y is equal to A transpose times x plus some differential element of x. Okay? But this is the same thing as saying, okay, y plus dy is equal to A transpose x plus A transpose dx. But y is equal to A transpose x. So we can kind of cancel. This leaves us with dy is equal to A transpose dx, or we can say that y with respect to x, which is basically dy dx, I'm going to put it in quotes, is just A transpose. All right. So then what we're saying is if y is A transpose x, and you take the derivative with respect to x, you get A transpose. I'm hoping that this is the first sign that some people who might feel a little bit lost in this lecture, this is the first sign of something kind of normal happening. Because if I said that y is equal to 2x, this is all a scalar equation, right? Scalar equation. Then dy dx is equal to 2. Okay. If y is equal to a vector transpose times the vector x, then the derivative looks like we're just kind of dropping the x term, right? So that's, okay, the first sign that something kind of normal is happening here. Let's get some more examples going, and this is going to start to get easier and easier. We're already past the hump. The hardest stuff is behind us. Here's another example. Find dy dx, but in this case, they both have hats, for the case where y as a vector is some matrix times ax. Okay. Second verse, same as the first. So in this case, y plus some differential element of y is equal to the matrix A times the vector x plus some differential element of x. Okay? That's the same thing as saying y plus a differential of y is equal to A times x plus A times some differential of x. Cancel, cancel. Oh gosh, this is starting to look really familiar. Dy is equal to A dx, or y sub x, which you could think of as dy dx, is just A. Okay, so hopefully this passes a sanity check. It's the same exact idea. If y is A transpose x, where A is a vector, taking the derivative with respect to x just drops the x. Okay, same thing that we're used to with regular calculus. If y is a matrix times x, then taking the derivative of the vector y with respect to the vector x just drops the x again, and we're left with A. Hopefully that's like, all right, things are getting a little bit better. Okay. Let's do one more example. This one's going to look a little bit hairy, but bear with me here. Now, example. Find dy dx. Notice only the hex has a little hat on it there. For the case where y is equal to x transpose ax. So A is a matrix, and it's being left and right multiplied by x to get you a scalar. Right? Now, before we go through this operation, and it's not going to be that many lines of math, I want everybody to write down in the margin what they think the answer to this is going to be, just based on your intuition, based on what we've seen so far. If y is little a transpose x, you take the derivative, you just have A transpose, which is familiar for like vector equations or for regular old scalar. If y is equal to ax, then dy dx is equal to A, right? That's the same idea that we're familiar with regular calculus. What I'm saying is this is a little bit like saying y is equal to ax squared, right? So if that were the case, I'm going to erase things now. What do you think the answer to this is going to be? And then you're going to wait with bated breath to see if we get the answer correct. So we're going to define a few things here. Let z be equal to x transpose, and let g be equal to ax, such that y is equal to zg, where z is a row vector and g is a column vector. Okay. The reason why is because now we can leverage the things we've already talked about in this lecture. So from our inner product discussion, we know that y sub x would be G transpose Z sub x transpose plus Z G sub x, right? So let's think about that for a little bit. If we say Z transpose plus some differential element of Z transpose, well, that's the same thing as X plus DX. So we can plug that in here. DZ transpose would then be equal to DX, right? Or we could think of it this way. ZX has to be, transpose, the identity matrix. Now, if that's not clear in a second, it's going to become clear. So bear with me here. ZX transpose is the identity matrix. Similarly, G plus DG is AX plus differential of X. So that means that DG has to be equal to A dx, or G sub X is just the A matrix. So we can think of it this way. The derivative of Z, which is just X transpose. The derivative of X transpose with respect to X is just the identity matrix. The derivative of X with respect to itself is the identity matrix. The derivative of AX with respect to X is just A. Okay, so that hopefully should make some sense. So if we're going to piece this back together, then Y sub X is G transpose I plus Z A. Or if we're going to go back to our initial setup, it's going to look like X transpose A transpose plus X transpose A. Or we could say that it is equal to X transpose A transpose plus A. Or, not for the punchline, then dy dx is equal to X transpose A transpose plus A, which, in my opinion, sort of looks like if you started with y equals x squared, or sorry, I guess it would be y equals ax squared, then dy dx is 2ax. So this is the vector form of that. So we've dropped the x, which is on the right-hand side, and now we have X transpose, A transpose plus A. So this is the matrix equivalent of saying 2A. We do have this transpose operation here. If it was a symmetric matrix, that'd be even better, right? It'd be just essentially 2AX. That's the idea. All right. So finally, the rest of the about 15 minutes that we have is going to be two examples, which are actually pretty darn useful for us. So we've got some kind of ethereal looking examples, and look, sure, the dy dx when it's a vector looks like this, so on and so forth. Let's get a little bit more concrete. All right, so let's do another example. It's a little bit more concrete. A Jacobian is a matrix which lets you know how a perturbation in X creates a perturbation in Y. So suppose some object has position x, we could think of as x1, x2, and x3. That's a column vector. Okay. Well, then in that case, the range from the origin to this object is the length of the vector x. So we're going to define it like this. Rho is equal to x, like this. It's technically it's the 2 norm of x. Or we could think of it as the square root of x transpose x. Or you could think of it as the square root of x1 squared plus x2 squared plus x3 squared. This is a little bit more concrete because we were just talking about the ranges of unknown vectors earlier today when we were talking about Gauss's method, right? Okay. We will write this as follows. Rho is equal to x transpose x, all of it to the 1/2 power. That is the preferred main 6964 way of writing this equation. And you're going to see why in a second. Right? So the Jacobian, which is the derivative of rho with respect to x, tells us how changing x affects rho. Okay, so you can think of it this way, right? Some differential in rho, which is a 1/1 scalar, is d rho dx dx. So we know that this is going to be a 1/3 because we know that dx is going to be a 3/1. And this is the same thing we were saying before. The derivative of a scalar with respect to a vector, in this case a column vector, is going to give us a row vector. So the same thing, nothing new from what we've talked about before. Let's actually do it now, right? So say the partial of rho with respect to x is equal to what? Well, actually, let me rewrite this. I'm going to bring this top equation down here in a minute. Rho is equal to x transpose x to the 1/2 power. So then in that case, the partial of rho with respect to x, got to think about the chain rule, right? First, the exponent comes out front. Then the interior stays unchanged. Then the exponent drops down by 1. So 1/2 minus 1 is negative 1/2. And finally, we have the derivative of the interior. So the derivative of the interior is going to be the derivative with respect to x of x transpose x. Okay, so that leaves the question, what is the derivative with respect to x of x transpose x? So here's the way we're going to write this out, right? The derivative, over here, the derivative with respect to x of x transpose x. What I'm going to do is I'm going to shoehorn in a matrix to this. This is the same thing as the derivative with respect to x of x transpose identity matrix x, right? Because you're allowed to shoehorn in the identity matrix the same way you're allowed to multiply by 1 in a scalar equation as much as you want, right? Same idea. But now, if we follow the principle we saw before, wouldn't this just give us x transpose I plus I transpose, which simplifies to just 2x transpose, which makes sense, right? If y is equal to x squared, then dy dx is just 2x. If y is equal to x transpose x, then dy dx is just 2x transpose. So you're kind of dropping the x from the equation, right? So let's round this out because we're almost done with this example here. There we go, almost done. In this case, then, if we kind of substitute this back in, then d rho with respect to dx is equal to what? Well, it's 1/2 x transpose x to the negative 1/2 times 2x transpose, where this 2 is going to nicely cancel this 1/2, or the derivative of rho with respect to x is just 1 over rho x transpose, right? Because x transpose x to the negative 1/2 power is just 1 over rho. So that gives us this. There we are. So this example and the next example, which should take about 5 minutes, and I can let you go at the top of the hour, are perhaps confusing now. We can talk about them later if we want to make them make more sense. But these are absolutely going to be things that you find yourself referring back to in future homework assignments. I think this is going to be very useful. So remember, the problem that I promised we'd be able to solve by the end of class is this. Our example. Two-body motion linearized about some reference trajectory. Right. So first, I want to notice something. R double dot is equal to negative mu over R squared, cubed R is super duper nonlinear. Okay, so now in state space, which we're familiar with because we already put the two-body equations of motion into state space for homework 1, we're going to say that x, which is our state, is r and r dot, or v. Okay, so then x dot is equal to what? Well, it's going to be r dot and r double dot, which if we want to work this out is going to look like this. I guess if we think of this as being x1 and x2, then r double dot, which is x1 dot, is just x2. And then this is going to be negative mu over x1 squared x1. So there's our state space of the equation of motion. Here's what we're after, right? We want to know the Jacobian of this. We're going to linearize this system. So we seek to know the derivative of x dot with respect to x, which involves finding the derivative of r double dot with respect to r, which was our initial problem that we used to motivate all of this, right? So I guess we could say this. The 6x6 matrix dx dot dx can be broken up into 4 3x3s. So we're really saying what is dx1 dot with respect to dx1? What is dx1 dot with respect to dx2? What is dx2 dot with respect to dx1? And what is dx2 dot with respect to dx2? They should all have little vector hats on them. So there's 4 derivatives that we need to do here. Let's start with an easy one. The derivative of x1 dot with respect to x1, we're putting that back in terms of r and v. That's the same thing as saying, what is the derivative of r dot with respect to r? Let's just look at the equation, right? R dot is another one of the states. R dot has nothing to do with R. Therefore, this is going to give us a 0 matrix. We still need to maintain that it's a 3x3. Okay. Now let's take another one. what is dx1 dot with respect to dx2? Well, isn't that the same thing as saying dr dot with respect to dr dot? Well, the derivative of anything with respect to itself is 1, but this is matrix land, not scalar land. So this is going to give us the identity matrix. Let's do another one. What is the derivative? We're going to skip ahead here because the bottom left is going to be the problem one. The derivative dx2 dot with respect to dx2, well, that's the same thing as saying, what is the derivative of acceleration with respect to velocity? And if you just look at the acceleration equation, velocity is not in there, right? So 0, 3 by 3 again. So here comes the scary one. And this is what we've been practicing for, right? All of it leads to this. The derivative of x2 dot with respect to x1 is the same thing as the derivative of r double dot with respect to r. All right, here we go. So what we're going to do then is we're going to say find the derivative with respect to r of, well, we got to write out our equation first. Let's start with this. We're used to seeing the two-body equation written this way, right? We're used to seeing r double dot is equal to negative mu over r cubed r. But let's write this out. I don't like this normalization. It's like, how the heck do we take the derivative of something that's been normalized? I'm going to write it like this. R double dot, so we're just going to rewrite this, is equal to negative mu, and then in parentheses, r transpose r to the negative 3/2 power times r. The exact same equation, but now it's written in terms of fun exponents instead of fractions and stuff like that. So now, if we have that, it's going to be a little bit easier. The derivative of r double dot with respect to r is going to be, okay, we got some chain rule stuff going on and some multiplication rule stuff going on. This is going to be a little bit ugly. So one thing at a time. First, it's going to be negative mu, and then it's going to be negative mu times negative 3/2 r transpose r to the negative 5/2 times whatever the derivative of the interior would be. So that would be d with respect to dr of r transpose r, right? And that's going to give us, oh, can't forget, we've got our r, there we are. Okay, good. And then we also have us. So it's the first term times the derivative of the second term plus the second term times the derivative of the first term. So the next one's going to be really easy, right? It's going to be negative mu r transpose r to the negative 3/2 power. And then we just drop the r, right? The derivative of r with respect to itself would just give us the identity matrix, 3 by 3 identity matrix. So the derivative where we're, kind of holding the first bit constant and taking the derivative with respect to r is trivial. The first part is a little bit more complicated. Let's tidy this up a little bit. Remember that the derivative with respect to r of r transpose r is 2r transpose. So the derivative of r double dot with respect to r looks like this. Okay, we've got a negative, and those cancel out. So it's 3 mu over 2 r transpose r to the negative 5/2 power times 2, oh, can't forget our r from before, 2r r transpose, where this 2 now cancels out with this 2. All of that minus mu r transpose r to the negative 3/2 times the identity matrix, 3 by 3 identity matrix. Okay. So to try to clean this up a little bit, almost done, d r double dot with respect to dr is equal to 3 mu over r to the 5th times r transpose minus mu over r to the 3rd times the identity matrix. and we're going to define this as G so that we can actually answer the question. So that means that the derivative of x dot with respect to x is equal to 0, 3 by 3, I 3 by 3, this G term that we just computed, and then 0, 3 by 3 again. So to be clear, this G is this G. And this is going to be a 6 by 6. All right. That is our discussion of matrix vector calculus. I apologize, we had to go through that a little bit faster than I would have liked to, just to get it done in the time that we had. If I had my preferences, we would have stopped for more questions, and I would have posed some of these as, open-ended examples that I'd like you to solve on your own. So apologies, we had to rip this one off like a Band-Aid. There is our discussion of matrix vector calculus. I would definitely encourage you to come back to these notes and review them if you have any questions. And especially these last two examples are absolutely going to be useful for some of your homework assignments. And they're examples that I used when I was writing the homework assignments. So you're going to want to make sure that this hopefully makes sense. I'm going to stick around as long as y'all need to answer questions, but I'm going to stop the recording now. And yeah, thanks everybody, and y'all are dismissed.